Team Liverpool. This is our presentation on the Mars Rover suspension system. This is our table of contents. This is the introduction. In this project, we must design, analyze, and optimize the suspension system of a Mars rover. The rover has a suspension system that is able to withstand the static and fatigue failure that may be encountered on the various landscapes found on Mars. The outcomes of this project are: calculate the value and the location of the maximum stress in the suspension system, and check for the static yielding and fracture. Calculate the fatigue resistance for the suspension system, and make an optimized design as lightweight as possible, which meets the safety requirements.
Assumptions. The assumptions we use throughout the project are: the angle between the shock and the tube does not change, the tube does not deflect, we assume small strain, minimum stress is 0, the material throughout is uniform or homogeneous, there's no torsion, temperature effects are negligible, and forces in the x direction are in equilibrium. This is our free body diagram, reaction forces, along with our shear diagram, stress distribution diagram, and our moment diagram. For our knowns, we have a design life of 500,000 cycles, a max force of 850 pound force, a minimum force of 0 pound force. Our D, as shown earlier, is 4 inches. Our length of the tube is 12 inches. We have a standard hollow tube. It's a 1050 hot rolled steel, and the angle of the tube and the force applied would be 75 degrees. For our unknowns, we need to find out our tube dimensions, our fatigue safety factor, our cycles to failure, our endurance limit, our max normal stress, our max shear stress, our von Mises stress, our yielding safety factor, and our critical locations of our stresses.
We solved our equilibrium equation and found the max force in the y direction, and we then found our modified endurance limit. Using Soderberg's fatigue factor of safety equation, we were able to derive our fatigue factor of safety equation and determine our cycle to failure. On the right, we solved these equations using the dimensions we found, which is explained later, and there is no yielding as shown at the bottom.
Optimization. As shown in the previous slides, we had one equation with two unknowns, which would be virtually impossible to solve. Therefore, we combine I, the second moment of inertia, and dO, the outer diameter, into one variable, U. Afterwards, using Appendix A8, comparing the ratio between I and dO, we found our percent difference to find the most optimal dimensions for the hollow shaft. Here is our mathematical file and our Excel file showing that 1.5 outer diameter, 1/4 thickness is the most optimum dimensions.
This is our conclusion. We first drew a free body diagram of the tube and suspension, and then determined our knowns and unknowns. We then found that the forces in the x direction would not affect our design, and the forces that would were in the y direction. We used our moment and shear diagrams to determine its location. Through using Soderberg's fatigue factor of safety equation and the standard dimensions for hollow shafts, we compared the ratio between the second moment of inertia and the outer diameter to find the dimensions for the hollow shaft. We used our new dimensions to check for yielding, find cycles to failure, and determine our fatigue safety factor. We then optimized our dimensions and found them to be 1.5 inches for our outer diameter and 1/4 inch for our thickness, and we believe they are reasonable since the factor of safety was 3.24. And the other standard dimensions above and below this were either under the safety factor or over-designed. One of the biggest challenges was that we started with an equation with two unknowns but combined both variables into one to solve for it. We also found it challenging to decide on which k factors to use for our modified endurance limit.